From rising seas to rising temperatures, the world's current climate has left many challenges for generations to come. This week, we explore stories about our changing climate and how we can survive to adapt. You're watching Cheddar's Who Knew? I'm Hana Ostapchuk. Anyone who remembers the 70s and 80s will probably remember acid rain. But anyone who follows environmental news will be surprised to learn this. We solved it. Well, kind of. Here's Cheddar's Karen Jed with the story.
Summer is fog season in San Francisco. These thick layers of fog are chilly and damp, but they won't deter determined runners or cyclists. The 70s and 80s, however, were a different story. Back then, the fog was often 10 to 100 times more acidic than it should be. SoCal was even worse, with fog closer to the acidity of lemons than typical water. Acidic precipitation like this was a huge global problem. Although if you've heard of it, it's probably acid rain. Sorry, fog. Acid rain wreaked havoc around the world. It rendered lakes inhospitable, killed forests and crops, and even corroded Mayan ruins. Not to mention the effects on human health. But today, acid rain is behind us. We solved it. It's an environmental crisis story with a happy ending. Mostly. Kind of. We'll get to it. Acid rain is exactly what it sounds like. Rain that is more acidic than it should be. We measure acidity using the pH scale. More acidic over here and less acidic over here. Pure distilled water is right in the middle with a pH of 7. Moving from one number to the next is a tenfold change. So pure water is 10 times less acidic than milk and 10 times more acidic than ocean water. And normal rainfall is actually right here, which I found confusing, so I called in reinforcements. I spoke to a science teacher with a master's in chemistry and atmospheric sciences from MIT, who's also my sister.
So it turns out that normal rainfall isn't perfectly neutral because normal rainfall has other chemicals in it. Carbon dioxide, CO2, is the thing that's responsible for even normal, unpolluted rain to not be perfectly neutral pH water. But it's not a concerning amount of acidity.
But you know what was concerning? When in the 1960s, scientists started finding rain with pH levels as low as 2.8 or even 1.7. Now, if you think you know the root cause of all this extreme acidity, you're probably correct.
Pillars of smoke by day, pillars of fire by night, pillars of progress. Machines to make machines, production to expand production.
You know the story. Some countries started burning a ton of fossil fuels, which sent carbon dioxide emissions skyrocketing. But I'm actually going to put a pin in carbon dioxide for now, because while it is a culprit in this story, it's not the main culprit.
The two acids that started becoming the big problem are nitric acid, HNO3, and sulfuric acid, H2SO4. And so they are based on nitrogen oxides and sulfur oxides, which are chemicals that have specific known industrial sources.
For simplicity's sake, I'm just going to call the emissions themselves NOx and SOx, and their respective acids, nitric and sulfuric acids. Okay? Speaking extremely generally, SOx arrived on the scene first, thanks to the really sulfur-rich coal that drove the first wave of the Industrial Revolution. NOx came a little bit later because it primarily comes from the burning of gasoline by power plants or cars. But both sulfuric and nitric acids are way stronger than carbonic acid. So as more and more of them piled up in the atmosphere, the water up there became increasingly acidic. But it took about 100 years, give or take, for anyone to notice. By which I mean the scientists noticed, and probably people living in affected areas noticed. Acid rain was killing forests, fish, and crops. It was making normally cloudy lakes eerily clear. It was corroding buildings, and it was exacerbating heart and lung problems. But the first real attention acid rain got came in a 1967 edition of this Swedish newspaper, Dagens Nyheter, courtesy of this Swedish scientist, Svante Odin, in an article entitled "An Insidious Chemical Warfare Among the Nations of Europe." I'm sorry to all the Swedes. In it, Odin blamed emissions from other European countries for acidifying Swedish rain. Now, this got a lot of Swedes in a tizzy, but it still didn't make major waves much beyond that. Because at that point in time, scientists had yet to prove something that seems kind of obvious in retrospect, that pollution can move.
If you think about the problem of soot, for example, those are particles that are like visible to the eye, right? But the thing to know about gases is that particles of a gas are like a molecule, like unimaginably small.
Meaning NOx and SOx can drift a long way from their sources. But we didn't have concrete proof at the time. Previous research had already found that nuclear fallout can cross continents, and that pesticides can make it as far south as Antarctica. But what types of pollution could travel and how far was still up for debate at the time. So throughout the 1960s and 70s, scientists all over the world are working really hard to pile up evidence that, yes, emissions of NOx and SOx are causing acid rain, and that, yes, they can travel really far from their industrial sources. So slowly but surely, more and more people boarded the acid rain train, or rather the anti-acid rain train. But if you follow environmental news, you know what comes next.
But more importantly is the issue of whether further control of SO2, which is a specific pollutant and one dear to the coal industry, will in fact make any reduction in the acidity of rainfall.
That's William Poundstone, a major coal industry executive. In this clip, Poundstone is debating a top EPA official, Douglas Kossel. The whole show is linked below if you want to check it out. Poundstone exemplifies the strategy of the fossil fuel industry at the time. Sow doubt about the science of acid rain, and warn about the dangers of moving too quickly to curb emissions. And the industry found strong allies in the renewed conservatism of the Reagan and Thatcher administrations. The US Congress rejected 70 bills about acid rain during Reagan's tenure. And fair enough. Limiting emissions didn't seem all that appealing after 150 years of transformative economic growth, not to mention the energy crises of the 1970s. But by the 1980s, the situation was becoming pretty hard to deny.
On one occasion here, an Englishman caught 80 salmon in a single day. Now, thanks to the effect of acid rain, only 4 have been caught in a year. And this is southern Norway's cleanest river.
On issues like acid rain, the White House has turned down action.
In Germany, it's alleged that half the country's forests have been damaged by acid rain.
There are tons of examples to look at here, but I want to focus on Canadian lakes. Emissions from the coal-happy US Rust Belt did not respect Canadian sovereignty. They drifted across the border, acidified Canadian rain, and rendered a lot of lakes inhospitable to life. It quickly became much more than an environmental problem. It ballooned into a thorny political spat that the Los Angeles Times called the single greatest irritant in US-Canadian relations. When Reagan visited Canada for the first time as president, he was greeted by thousands of protesters shouting, "Stop acid rain." Finally, from the mid-80s to the 1990s, enough political pressure mounted worldwide that countries took action. European nations got together to pass protocols limiting SOx and NOx emissions in the 1980s. In the US, President George H.W. Bush updated the Clean Air Act in 1990 to implement a cap-and-trade system for reducing emissions. Power plants that used cleaner fuel sources like low-sulfur coal or filters that trapped emissions could sell their allotment of emissions to other power plants. Oh, and Canada and the US became friends again to sign an emissions reduction agreement in 1991. And it worked. Emissions in both North America and Europe plummeted from the 1980s through the 2000s. I told you this had a happy ending. Kind of. Yes, the countries that had already enjoyed 150 years of burning as much coal and gas as they wanted, they cut emissions. Although some worry that levels are still too high for affected environments to recover. And in other countries that began industrializing more recently, emissions of NOx and SOx are still increasing. But remember how I put a pin in carbon dioxide at the beginning of this video? It's time to unpin. Everyone's heard of carbon dioxide as a potent greenhouse gas that traps heat and warms the planet. But now, enough of it is piling up in the atmosphere that it's becoming a potent acidifying force. Not of rain, but of oceans and lakes. We've known about the ocean problem for a bit, as the average acidity has increased by about 30%. But more recently, new evidence suggests that the same thing is happening to freshwater lakes. I mean, we just can't win. Reducing carbon dioxide emissions kind of feels like the final boss battle in a video game, so hopefully we can do it.
If you feel yourself getting unbearably hot in a city over the summer, know that you're not alone. In fact, cities can often be up to 15 to 20 degrees Fahrenheit warmer than nearby suburban and rural areas. This spells danger because this heat is particularly deadly. Here's why.
Have you heard the one about the frog in the boiling water? Put a frog in a pot of boiling water and it will leap out. But put it in cool water and slowly heat it up, and it'll boil to death. That's not literally accurate. The frog would definitely try to escape in either case. But metaphorically, this scenario is playing out in all of our cities, just over years and decades, not minutes. You may be thinking, but Cheddar, isn't the whole world getting hotter? And yeah, you're right. But of all the Earth's surface, cities are getting the hottest. And for the vast majority of us who live in cities, this spells danger, because extreme heat is the deadliest of all weather hazards. Even our one respite from the heat, cool nights, is disappearing in urban areas. And unlike the frog, we can't leap out. There are clever solutions to cool our cities, which could work if we move quickly. Otherwise, barring rapid expansion of these guys' new hobby, we're stuck here. There's nowhere to go. Images like these are really shocking. But in terms of overall deadliness, extreme heat beats them all.
Turning now to a dangerous and unprecedented heat wave.
The death toll estimated at nearly 200. Homeless people among the hardest hit.
The exact mechanisms of heat deaths are complex, but they boil down to two types. The first is heat stroke, which is directly attributable to heat. In short, the body can no longer cool itself down, which can trigger central nervous system dysfunction or even multiple organ failure. There's also a phenomenon called wet bulb deaths, which is where a combination of heat and humidity makes it so that sweat can no longer evaporate.
We need to keep our temperature in this narrow range, right? We're not reptiles. So the way we do it is through sweating. But if there's too much moisture in the air, I can't effectively sweat.
The second type of heat fatalities are called excess deaths.
So excess deaths are people who die due to pre-existing conditions that are exacerbated by heat.
Often, those won't be listed as heat-related deaths, but the extreme heat loaded the dice, turned up the risk.
Ironically, it's the increasing heat after the sun goes down that could be the most dangerous. At night, dense materials release the heat they absorbed during the day, which is causing a dramatic increase in nighttime temperatures and stifling our chance to cool down.
And it's the nighttime lows that don't get below 86 degrees, which is kind of the average skin temperature of humans, so the body can't have a chance to cool back down.
So why does this happen in cities? 3 words: urban heat islands.
The concept of urban heat islands is very simple.
Things that are more dense take longer to heat up and then longer to release that heat back into the environment. And so bricks, concrete, steel are all very dense materials.
Whereas in a forest or a meadow where there's a lot of surface and a lot of moisture on those surfaces, a lot of the sun's energy, instead of directly warming things up, will be evaporating some of that water, which is a process that doesn't create as much heat.
To put it very simply, the sun's energy has roughly 3 options when it reaches Earth. 1. Become an ingredient for plant photosynthesis. 2. Evaporate nearby water. Neither of those cause much of a temperature rise and can even cool down an area by providing shade or putting water into the air. The trouble comes with option 3. Heat up whatever other materials are around. And in cities, especially dense ones like New York, there are a lot of other materials. Just look at these maps. See the near-perfect overlap of vegetation and cooler temperatures? This also highlights the disparities between neighborhoods. Note how the coolest neighborhoods with the most vegetation are also the wealthiest. So even though greenhouse gases heat the world roughly equally, cities, and especially poorer neighborhoods, are often hotter than suburban or rural areas by up to 15 to 20 degrees.
It might be the same amount of warming in the city as the surrounding areas, but because the city's starting from a higher baseline, there's more risk.
This is already evident in New York, which was recently reclassified from a humid continental climate to humid subtropical.
The number of days above 90 degrees Fahrenheit will triple towards the end of the century. And so, New York City is going to start feeling more like Birmingham, Alabama.
Speaking of Alabama, their state flower, the camellia, is now successfully growing in New York. We've known about UHI for a long time, as far back as the early 1800s, when amateur meteorologist Luke Howard began comparing temperatures in London to the countryside. But we put the matter on the back burner for nearly 2 centuries.
It hasn't been until about the 1990s when climate change was really being brought into the conversation that we started looking at the urban heat island effect.
But now, the situation seems to be coming to a boiling point. Since it's unlikely that everyone will move elsewhere, cities need ways to turn down the heat. Fortunately, there are many solutions. First, trees.
Trees that can provide shade, and they can evapotranspire moisture into the atmosphere, which also reduces the heating.
Unfortunately, the US is losing trees at an alarming rate, about 36 million per year. This is why the first part of New York's plan was planting 1 million trees between 2007 and 2017. The second solution takes place well above the trees, on rooftops.
So cool roofs are essentially a white or refractive surface on a roof, and so it doesn't absorb as much energy.
But when you cluster these cool roofs in close geographic proximity, you can actually start seeing a reduction in neighborhood temperatures and ambient temperatures. So we've already coated 10 million square feet of rooftops across the city, and our goal is to continue to coat 1 million square feet each year.
In addition to reflective paint, building owners can reduce heat by installing rooftop gardens or solar panels. There are a few other strategies like opening cooling centers, prioritizing lighter construction materials, and deploying tens of thousands of air conditioners to vulnerable people, which is what New York did to protect low-income residents during last summer's stay-at-home orders. Ultimately, though, there's only one way out of this. You know what's coming. It's a climate change video. We have to talk about it. Reducing greenhouse gas emissions.
So I do have confidence that we could quickly bend the curve towards reducing far less emissions, but I have to be honest and say that I'm not totally optimistic. But unfortunately, how quickly climate change is happening, how quickly we're seeing extreme, long-lasting heat waves. There, I think it's very hard to be optimistic because it looks to me like things are happening a lot faster than our climate models predicted.
Globally, our planet is already 1.1 degrees hotter than it was 150 years ago. But most scientists agree that an increase of just 0.4 degrees will drastically change the world. Here's Cheddar's Hana Ostapchuk with the story.
When we talk about climate change, there's one number that comes up a lot.
The goal seems to be to limit warming to 1.5 degrees Celsius.
1.5 degrees Celsius.
1.5 degrees.
It may sound arbitrary, but it's not. Every 1/10 of a degree matters. Here's why. In 2015, 193 parties signed the Paris Agreement. In doing so, they agreed to pursue efforts to limit the average global temperature increase to 1.5 degrees Celsius, or 2.7 degrees Fahrenheit, above pre-industrial levels. To be clear, our planet is already 1.1 degrees hotter than it was 150 years ago. But most scientists agree that an increase of just 0.4 more degrees will drastically change the world. However, it would continue to be livable. Things do get murky, though, as the projections increase above that. Here's the difference between 1.5 and 2 degrees of warming. Sea levels have and will continue to rise. With a 1.5 degree increase, 69 million people will be directly affected by rising seas. 0.5 degrees more, and that number increases to 80 million. At 1.5 degrees warming, about 14% of Earth's population will be exposed to deadly heat waves at least once every 5 years. 0.5 degrees more, and that number jumps to 37%. About 61 million more people would be exposed to severe drought in a 2 degrees Celsius warmer world than at 1.5 degrees warming. If the average temperature increases by 2 degrees, we would lose double the amount of plant and animal species, triple the amount of insect species, and 99% of our coral reefs. We can also expect a substantial increase in the frequency of extreme weather events. Lastly, it's important to remember that these numbers are global averages. Different areas of the world would fare far worse than others. Of course, much damage is already done, but scientists agree that we still have time to minimize the worst of it. That is, only if we keep temperatures from rising higher than 1.5 degrees. So can it be done? Only if we act fast. Scientists say the target can only be met if global emissions are reduced by 45% by 2030 and cut to zero by 2050. It's a lofty goal, but most agree that there is no alternative.
That concludes this week's Who Knew? I'm Hana Ostapchuk. Thanks for watching.